Hello, Math 135. This is Tracy. We are in chapter 10, and we are going to conduct another hypothesis test. The problem we have before us. An article published in USA Today stated that in a study of 200 colorectal surgery patients, 104 were kept warm with blankets and IV fluids. 96 were kept cool. The results show only 6 of those warmed developed wound infection versus 18 who were kept cool. Use a 0.05 significance level to test the claim that warmer surgical patients recover better. What are the implications? So we are conducting a hypothesis test. It's pretty obvious when it gives us a significance level and says test the claim. That's what hypothesis testing is. So what kind of a hypothesis test are we conducting? We are looking at 6 out of 104 versus 18 out of 96. This is a proportion because what we do is we take the number of successes, which in this case is not very good. A success is getting infections. But we take the number of successes divided by our sample size, and that's a proportion. These patients either get an infection or they don't. And we have at least 6 failures and at least 5 failures and at least 5 successes in each group. 6 out of, what were the warmed? 104, 6 out of 104 successes, which means we had 98 out of 104 failures. Both numbers are greater than 5. We have 18 out of 96, 18 successes, which means that we have 78 failures. So we can use our procedures. So let's go ahead and do it. So here's a reminder of what the article said, and what is it we are testing? Well, we already said 2 population proportions. On our TI, we go into Stat, Tests, and this is a 2 proportion Z test. 2 proportions is always 2 prop, and proportions is always a Z test. Our random variable, again, is going to be the difference between the 2 sample proportions. The P prime W minus P prime cold. The proportion of those kept warm minus the proportion of those kept cold. Actually, it doesn't matter what order we do our difference in. We could subtract the other way. And in each sample, we're looking at the proportion of infections after surgery. Our hypotheses. Our null hypothesis, as with all hypothesis tests comparing 2 different samples or matched pairs, is that there is no difference. Our null hypothesis is that the 2 proportions are the same, or that the difference between the 2 proportions is equal to 0. And again, it doesn't matter how we choose to write this. Our alternative hypothesis, warmer surgical patients recover better. Warmer surgical patients recover better. Okay, but what does that mean in terms of proportion of infections? Recovering better means no infections. So the group with fewer infections would be the group that recovers better. So we are claiming that the proportion of infections in the cold group, PC, is greater than the proportion of infections in the warm group. The group kept cool has more probability, more percentage of infections than the group kept warm. That's because the warmer group, we are hypothesizing, recovers better. So that's how we write it. Our alternative hypothesis, PC is greater than PW. Or we could write it the other way, PW is less than PC. Or we could write the difference, PC minus PW is greater than 0, because more infections if you're cold, bigger number, minus fewer infections if you're kept warm, smaller number is greater than 0. Doesn't matter how you write it, just be consistent. So we need to figure out what goes into our calculators. Just like before, we need to pick a group to call group 1 and a group to call group 2. So let's let the cold patients be number 1 and the warm patients be number 2. Why? Yeah, I have no idea. Just pick one, it doesn't matter. You could have picked the ones that came first in the problem, or doesn't matter, just be consistent. So cold patients are number 1. X1 is the number of successes in the first group. So successes are infections. So we have 18 infections out of 96 sample size. X1 equals 18, N1 equals 96, 1 because it's the cold group. In the warm group, we have 6 who developed infections, so 6 successes, X2 is 6, and the sample size was 104. So N2 is 104. And our claim is that the number of infections, the proportion of infections in the first group is greater than the proportion of infections in the second group. So P1 is greater than P2. That is the claim that we are testing. In your calculator, as we said, fill out everything. And then when you highlight calculate and hit enter, we get the bottom left screen. So you can see what we're testing. The proportion of successes in group 1 is greater than the proportion of successes in group 2. Ignore the Z statistic. We are not fiddling with that. P equals is our p-value. So our p-value is 0.00238, yada, yada, blah, blah. No e to the negative anything, so that is just plain what our p-value is, between 0 and 1. Perfect. Exactly where it should be. Notice we've gotten our sample proportions. If we were to divide out our fractions, our 18 divided by 96, we would get 0.1875. If we were to do our 6 divided by 104, we would get p hat 2. P hat and p prime are both ways of saying sample proportions. So p hat 2 is 0.05769, blah, blah, blah. And this is telling us that the proportion of infections in our patients who were kept cold was about 18.75%. Percentage of patients who were kept warm that got wound infections was about 5.77%. This is a difference of almost 13 percentage points. That's kind of a big deal. But the hypothesis testing says, is this something we could have gotten by chance alone if the groups were still really the same? And the answer to that is probably not. The probability of having 2 samples with so much of a difference between them, so much larger of a proportion for the cold patients getting infections than a proportion of warm patients, so much that the probability of getting so much of a difference if these 2 groups are actually the same is only less than 0.25%, 0.238%. That p-value of 0.00238, the probability of these 2 samples having such a big difference just by chance, if the groups are really the same and we just got freaky samples, is tiny, less than 0.25%. Tells us, well, again, significance level here, yeah, we've got alpha equals 0.05, but any reasonable significance level, our p-value of 0.00238 is less. And that means that the probability of getting our results are more extreme, just by chance, if the 2 groups are actually the same, is tiny. It's small enough that we really are going to doubt the null hypothesis. We are more inclined to think that the alternative hypothesis is likely. We reject the null hypothesis. Our p-value is less than alpha. But now we need to put it into words that a layperson could understand. Our data support the claim that warming surgical patients helps them recover better. We have sufficient evidence at a 5% significance level, p-value equals 0.00238, to support the claim that a smaller percentage of surgical patients that are kept warm get wound infections than surgical patients who are kept cool. Seems like we should warm surgical patients so that they are less likely to get infection and they recover better. Okay, So this was, I think it was section 10.3. Is that our section for? Yes, 10.3, comparing two independent population proportions. And we will do another example in the next presentation.